Hello and welcome back to another episode of the Oxford Online Maths Club. My name's James and this week I'm joined by Marcella.
Hi everyone, hello, good afternoon, boa tarde. How are you guys doing? I'm Marcela. I am the PhD student in the computer science department, and I'm really excited for this live. Oh my god.
It's going to be a lot of fun. It's another computer science. Are we saying takeover? Are we saying Oxford Women in Computer Science found more CS to tell us about, which we're excited for as always. Hello to people joining in Slido chat as well. It's me in the top square there, Marcella, and then underneath it could be you. If you're watching live, you can join slido.com/OOMC or go to slido.com and put in OOMC or click the link on the Maths Club website. Advertise the Maths Club website. If you found us via the magic of YouTube, then hey, well done YouTube for doing that. We also have a website where you can get not only links to previous episodes, which are on this YouTube channel, but also further reading notes. Not for this one because the further reading notes go up after the episode, usually the day afterwards, but sometimes. Last week I was really busy, so the further reading notes for quantum logic have only just gone up yesterday. But recent episodes have included Morse code with Eliane, Rabbits in Computer Science, which was with Euler, Euler and Oxford Women in Computer Science Society, looking for prime numbers in Pascal's triangle, some stuff with spherical geometry is what we've been up to recently. I always like to start by asking how people's day was. So hello in chat to Aaron and Anonymous and Hector and Anonymous and Joe. You can be anonymous in the Slido chat. It's one of the things I like. Here's a vote for how's your day been? Marcella, how's your day been? On a scale from 1 to 5, those are the options.
Five, for sure five, for sure five.
5, right? Having a good day. What's happened today? What's
Well,
if I
as,
can ask?
as a normal day of a PhD student, there is always like some pressure on the background, things going on, and sometimes we get so busy and so worried about so many things happening in parallel. And today I was just like, okay, you know what? I'm going to the department. I'm gonna watch this documentary with my colleagues about it's called I think it's like the breaking game, the theme game, but it's about Demis Hassabis, the person who got the Nobel Prize last year for chemistry, and he used neural networks to solve the folding problem, and it's somehow related to our lecture today. It's like something so simple like networks, if you put them together, you can actually like get a Nobel Prize. How exciting is that? So yeah, I like after the documentary, I was like floating in space, you know. I was like, wow, I'm so glad I watched that, and we're gonna talk a little bit about it later today. So yeah, five.
Fantastic. Chat's having a kind of 3.9 day on average. Last week we asked you how many ways there are to have an average of 4, and there's a comment on last week's YouTube video if you want to find out an approach to answering that question using hyperplanes. So if you like high dimensional data sets, then you might like that. Let's get some slides ready while we're going, because you sent me some slides like that. So if I'm on the right. Oh, hey, slides, brilliant. Oh, someone's just checked in to give us saying they're having a 2-star day. I'm always looking out for people who vote for 1-star or 2-star. It means they're having a terrible day, but there's some chance that we do some maths and that makes their day better. That's the plan. Can't really get worse, except if you're at 2. I suppose there's one way it could get worse, and we will try to avoid that. Mary says something in Portuguese, I think.
Cute.
Yeah, good, right, okay. I was going to read it out and then I thought, no, I'll just leave that there for you. Right, networks. We're going to talk about networks. You want to tell us about models of networks and things to do with networks. These are your slides. I've got the next slide button, so
Okay.
tell me when to move on.
Okay, so actually my research now on the field, it's on modeling how we make models better, how we can find ways that instead of guessing for parameters, we can actually use some statistics to come up with the best parameter set. It's not actually related to networks, however, and somehow everything nowadays is related to networks. And one way that we can find a best distribution of parameters for models, like models that are like that have random behavior, one of ways that we can do that is actually using networks. But then we need like teach the networks how to process information. A lot of very interesting things happens when we put like networks in layers, which is like neural networks and deep networks and things like that. So this is I thought would be interesting to bring some ideas about networks on this presentation. I think like at some point people on high school or even like in elementary school, they had to do some coloring, some painting, some connection. So I think it's a very interesting topic that's like in our everyday lives, but can get really interesting and also complicated. Yeah.
Nice. Okay.
Yeah.
I'm
Yeah.
really
Okay.
excited.
Yeah.
So this is the kind of neural net stuff that, well, eventually this is that related as a concept, the kind of neural net stuff that I've heard about.
Yeah, yeah, it is. And it's like so it's like that was the thing that I was really like paying attention on this documentary I was watching before this live, which is like, oh my God, it's not possible that you connect dots and then they can solve and this can solve like an open problem in chemistry and biology. It's crazy. So I think if we do understand the basic idea really well, you can actually come up with your own ways to process information in networks.
Cool.
You can actually go to the next slide.
Thank you.
Yeah, and please, I don't know if you have the same feeling, but I one of the things that I love about Oxford is that like it's a very historical place, you know. Like I walked on the street and I was like, oh my gosh, Robert Hooke was here, like Holly was here, and now me, Marcela, straight from Brazil. I get so excited. But okay, back to the networks, and this is also has to do with my childhood in Brazil. So the first person who actually tried to put some formality on the study of networks and edges and the stuff was Euler, and I actually used a generative model, and I wrote the prompt like. Create an image of Euler as an Oxford student. That's how we got.
I've never seen a picture of Euler looking so young.
Yes, yes, yes.
I suppose the glasses as well. So it is an AI generated in Oxford. All right, lovely. Okay.
Yeah, and it's like an Oxford student, so he thought like, okay, so he was probably really young, and I loved the output, which is also generated by works, right? Like generative AI is basically put information on a layer of network, and then at the end you ask the network, hey, can you do that for me? And then the network goes like backtrack on how it was trained and come up with things like that. So Euler, he's from Switzerland. I actually visit the house where he was born, but this is for later. But he was like so famous, like so amazing, so great that he was invited to live in Russia as I think like a mathematician of the imperial family or so. And then like people had this this problem in the city of Königsberg. They wanted to know if it was possible to cross all those 7 bridges without repeating it. And then of course people would like as a pastime, they would try to go from A until G. They would try to cross, there's like a small island there, and they would try to do this crossing. And then Euler was like, wait a minute, maybe instead of trying to like scratch all possible papers we can have. How about we try to pretend that we are just connecting points. We just add edges to represent the bridges, and we have points representing the land. Can we find a mathematical way to show if it's possible or not? Because people are like, they would try themselves and they would fail. And it takes me back to Brazil, because in Brazil we have a similar problem, which is like connecting the houses with, it's always like we have to connect 4 houses with water, electricity, and sewage. It's like, yeah.
I know the
So
problem. Okay, yeah.
yes. So when I saw this later at college, I was like, oh my gosh, Euler was thinking about it like 200 years ago, but he was having the same issue. But if you go to the next slide, please. Yeah, Euler was actually while he was thinking about it, how to solve this problem, he came up with a couple of formulas, which they are so simple that they are mind-blowing at the same time. He started to think like, okay, how we expand a little bit this idea of connecting points with edges, and we can actually once we connect those points, we actually have this one two-dimensional thing, this object. Let's start to put colors on it. Let's try to actually predict or calculate how many faces object can have. And then he came up with this, I think actually is minus f. I'm sorry.
Minus e, I think. Sorry, I should have spotted this before. I think it's v.
Yeah, I only
e,
saw now. Yeah, I'm so sorry.
Right.
Oops, yeah. But he came up with this formula, and also with this maximum number of edges when you consider only n, which is like the number of nodes. But it's quite interesting. Like the simplicity is mind-blowing, and I think during this process of trying to solve the Collins bridge problem, I think he was doing something that all scientists actually dreams to do, which is like observing something on the outside, like observing something that is happening, something kind of in nature in this case, like some artificial thing going on. And then he like, okay, instead of trying to solve to this problem, I was trying to find a way that we can generalize. So for the number of faces, we have then the number of vertex minus e, which is the number of edges, and the f, which is the number of faces. This small thing there has to be 2.
So this is the vertices represent the things in the circles in your diagram. They're the
yes.
They're shrinking down all of the land mass to a single point. To say if you're on one of the islands, then I don't care where you are on the island. That's a point. You're on the island. That's your vertex. And I get the edges of the bridges. There's a question in the chat. What's the face? I know when you have a solid shape made out of squares and triangles, the faces are the kind of squares and triangles. What are the faces in that picture?
Yeah, the picture actually shows 2 kinds of problems we can have. When we look at this picture, the faces are actually we don't consider the circles faces. They are representing the vertex. So what we have here, it's actually 2 kind of problems that they are very kind of traditional when we are studying those things, which is, can we paint the faces in a way that 2 adjacent faces don't have the same color? This is like a very popular problem. There is always, like when we are studying this kind of problem, there is like a map or a drawing, and then we try to paint this drawing without having adjacent colors. The other problem we can have is the dots. Can we have dots that are connected but they don't repeat the color. So the dots here, they are just like very big, just to make this point that we can also have to try to solve this kind of problem when we have vertex, but your friends, like the vertex that you are connected to, should not repeat that color.
Oh, I shouldn't be writing. That's not working. So this has got 6 vertices. They kind of land masses from the original thing. The vertices are joined by edges and they enclose. I guess because it's a special sort of graph that you can enclose areas. Sometimes the edges might cross or do things, but because these edges don't cross, you can think of them enclosing these.
Yeah. This image doesn't represent the Königsberg Bridge. It's not a representation.
Oh, sorry.
No, this is not. No,
Oh,
yeah, it's a different one. It's just to show the point that we can. I'm sorry.
No, right.
No, it's just to show that while analyzing these problems, we can have this issue or this challenge to paint a map, for instance, without having adjacent color, or we will have the same kind of problem but applied to the vertex.
Right, I see. So if you show me a map or something or a graph with some points and some edges and some faces made of edges, like in this one, triangles and trapeziums on the outside face, then I'll always have, for a graph with no lines crossing, v minus e plus f is 2. And that's separate from, I see, so that's one of the things Euler knew about, but it's separate from, that doesn't help me cross all of the bridges, right?
No,
so
not yet.
Yeah, okay, not yet.
Not
okay.
yet.
Is that coming up? Sorry.
Yeah, it is.
Okay.
It is.
This fact, somebody's asked if they can prove it. How hard is it to prove? I guess they want to know that v minus e plus f is always 2 for, technically for planar graphs, ones that you can draw without any lines crossing.
It's possible to prove, and this is why I love Euler, and I think it's so fair that there are so many things after him because he did that. He actually proved that with his proofs he showed that what happens on the Königsberg problem, but also how we can generalize this. So yeah, there is a proof for that.
You can induct on the edges. I think if you draw one edge at a time, each edge either joins together to existing vertices, in which case it creates a new space in between, or it connects a new vertex to your graph, in which case v goes up, e goes up, and faces don't change. So either way, you change 2 things at the same time, and you stay at 2. So okay, this is just a fact about graphs that you can draw. Again, special planar graphs, ones that you can draw without things crossing. But this other fact you've got on screen. Sorry, I know you want to tell me about crossing all the bridges, but this number on the screen, so maximum number of edges, 3n minus 6, where n is the number of vertices, right?
Yes.
I'm going to sneakily change that to 3v minus 6 just for consistency. Sorry. Sorry. Yeah, 3v minus 6. Sorry. Yeah. That's me being cheeky.
The mathematicians.
Sorry.
Formality.
I had this with quantum mechanics last week as well. The quantum mechanics, they have lots of notation, some of which means the same thing. And my thing is, I just want to use the same notation if I can. Okay, so I don't think I know this fact, that when you draw a graph, maybe it's a fact about planar graphs, that the maximum number of edges you can have is not that many.
No, and this is actually only for planar graphs indeed. And
otherwise, you can just join everything to everything and get loads and loads of edges.
Yes, we will see a situation where it happens when we are interested to this phenomenon to happen. Like everyone is connected to everyone. But this is basically idea of how we can have one layer, like a planar graph, and how we can it's like something so simple can get really complicated, mainly when we have to like walk on those vertex is like how a very common question we have on the first year in computer science is like, okay, if you were there on the vertex 1, is there a way that, like the Königsberg Bridge problem, can you go to all the other vertex and you don't go to same vertex twice?
Oh,
And
I
sometimes it's
see.
the edge. So the problem can vary.
So
Yeah.
there's two different problems. I can visit all of the vertices in one trip, but I don't think I can visit all of the edges. I don't know, but I think there's a rule for this. Because now this one in the middle, I've got a bit of a dead end situation. You know, if I go down this edge, I'm stuck. I've already done that, all the edges there, but if not, I don't know. Maybe that's something that people have seen before. I don't know what people have seen in maths or something, but there's a rule for whether you can draw them. I think we're going to see that in a second, aren't we? I'm going to think about this maximum number of edges a bit though, because
Okay.
it feels like
Fair.
it should be. I don't know. It feels like something. Maybe Euler can do it. I'm sure, but
Yes.
so in this picture, if you've got maybe about triangles, when that 3 looks like a triangle fact to me. Right. Okay. I'm going to think about triangles. Do you want your next slides now? Or?
Yeah, actually, now that you talk about the triangles, it's also it's interesting that you said that because there, like us, the number of nodes get like bigger and bigger. Like just imagine if we are to put in a network on a graph structure, everyone on TikTok or on Instagram, like the number of nodes is huge. If every user is a node, it's kind of crazy. But we do want to understand like which people and like in TikTok are the most important ones. And then one of the things that we have to measure this, like the clustering coefficient, is actually counting how many triangles is that person connected to. So it was interesting that you talked about it. We will get there, yeah.
Yeah, it says if you've got 2 vertices, something's not right, because if you've got 2 vertices, you can have an edge between them, and that formula would say that you can only have 0. Something's not quite right. If I've got 3, then I can have 3. Maybe it's if v is greater than 2. Maybe. Okay. Let's look at it. Next one. Or not so much for who's important on. Sorry, chat's talking about Eulerian paths, so I'm going to let them do that. This one now? Oh yeah.
Oh yeah. This one is yeah. If we go a little bit further. Just to make sure that the previous formula is the bound, like is the maximum.
Well, I don't think it is, right? Because not for 2. Because if you've got 2, you can put an edge between 2.
Yeah, I think it has to be something that has the properties of the Euler graphs, which is a minimum. You can do like a trail that you can actually walk in. I believe there is some the graph needs to follow a Euler idea first, or a Euler rule, because indeed, like with 2 wouldn't be possible.
Are we just gonna do the? So there's a question in chat about Eulerian paths. Somebody watching live wants to know about Eulerian paths. I can't remember what slides you've got coming up. Are you going to tell them the punchline to when you can do the bridges of Königsberg thing? Or is that?
Yeah.
Okay, that's coming. Sorry, okay, I'm very keen to.
That's okay.
We're coming back to bridges, but I've seen your next slide's about Erdős and Bacon number and things like that. Should we go there?
Yeah. We can go there.
Okay,
yes.
let's go there.
Yeah.
Okay.
So this is also Paul Erdős and Kevin Bacon. As in Oxford, I just put draw them in Oxford. Yeah.
I love the fact it gives everyone the same classes as me.
Yeah, so we know now like the profile that the network thinks about like people in Oxford.
I love it.
And I love it, and it's always like they dress really well, they are always like I love it. So when we go a little bit further in time in history, a little bit away from Euler. We meet this guy, Paul Erdős. I say Erdős, but I don't know if this is the correct pronunciation. But he was one of the first people who tried to do something a little bit further than only having this planar map. He started to think about, instead of having actual edges, he wanted to understand about the probability of having this edge. So it's basically like if I am friends with someone on Facebook, or if I follow someone on Instagram, what is the probability that I will also follow another person? So Paul Erdős started to think about it, and he was like very, very productive about that, because he produced around 1,500 papers. So he was really into this thing about networks and connections. And then when we start to study about Erdős, there is always this joke of calculating your Erdős number, which is basically see how many co-authors do we need to reach each other. And I was thinking maybe we can try to calculate ours. Or we can, if you had a co-author, we can just see, like, you can put actually anyone you wish on the website, and it will try to calculate your Erdős number.
Shall we have a go?
Yeah, let's try it.
Okay, I've got the website.
Okay.
This is on Maths.inet. It looks at all the publications. So is the distance, like, if you've authored a paper with Paul Erdős, you have an Erdős number of 1, and then if you've authored a paper with somebody of that Erdős number n, then you have an Erdős number of n plus 1, and it's like the minimum over all possible paths or something.
Yes.
Who should we do then? Should we do me? I think I've got an Erdős number.
No, I think what we do there is, like, on the first time you can. Oh, I should have sent my full name. I don't know how my names are written in my papers.
Well, I know how my name's spelled. Should I put me in?
Yeah, put your.
Feels a bit like showing off, except it's not.
Okay.
You gotta go my middle name as well.
Okay. Can
we search? Select author. Oh, I've got to find myself. No, none of those. This is fun, isn't it? Give me 2 seconds while I find myself on this website.
Yeah, let me see. Let me try to find myself as well, because maybe. Wait.
I've got this to work before. I'm definitely
Sorry?
I've got this to work before. I'm definitely a real mathematician.
You are a person there, right?
I found myself.
Okay.
Took me a while. Right combination of. Yeah. Okay. So then it shows you, like, a connections, right?
Yeah, like the co-authors you have until you get like someone who was a co-author, and then a co-author, and then a co-author.
Yeah. So I wrote a paper with my PhD supervisor. My PhD supervisor wrote a paper with, I believe that's his PhD supervisor. That person wrote a paper with someone else in fluid dynamics. That person wrote, I think this is a review article or something, with George Lorentz, who is a mathematician who worked on lots of things, including the Lorentz attractor. I think that's him, possibly a different Lorentz. And Lorentz worked with Erdős. So you could go through the sequence. I'm not sure about this link, but never mind. Yeah, there you go. Okay, do we want to do someone else, or?
No, it's okay. I was trying to. I was wondering if we could find maybe from you and me, but let me see if I find my name here.
We should have checked how to spell our own names, shouldn't we?
Yeah, I was like, I was trying yesterday, like, to find my advisor. Let me see if I can find myself. Otherwise, Marcella.
The idea for films is that 6 is good enough. It's called 6 Degrees of Kevin Bacon. I don't think 6 is enough for all of mathematics, and maybe the scope's wider than that on the other side of Erdős. I don't think 6 is wide enough. And actually the scope's a bit wider, right? Because sometimes mathematicians publish papers with other people, like fluid dynamics people like me, are we really mathematicians? Yes, we are. But also computer science, like you can get out to biology. The kind of weird thing to think about is, well, on this graph on the right with Kevin Bacon in the middle, some of these people are older than Kevin Bacon. Some people with a Bacon number, the Bacon number of degrees of separation from Kevin Bacon, some people were never alive at the same time as Kevin Bacon. So the kind of question, if you go back through movies, can you get all the way back? Can you find people from like the dawn of cinema who eventually, via connections through people not born yet, were connected to Kevin Bacon? Can you do the same thing for mathematicians and Erdős? Can you find someone who was born hundreds of years before Erdős existed, who nevertheless had an Erdős number backwards in time by collaborating with someone, I guess, younger than them, and onwards through then? Yeah, so I think I've been corrected. The Lorentz attractor person's not someone in my chain of connections, possibly. Although the evidence in chat is that it's spelt differently, but maybe I'll go and look it up.
This thing of the Kevin Bacon is actually interesting because this 6 degree of separation was something that the scientists were saying in a lot of things, not only in Hollywood, but nowadays with the social networks, this number is even smaller. And then we actually, when I was studying that, people were trying to calculate the Obama number, and for me it was like, I don't know, only 2, I think, 2 or 3,
Oh my goodness.
which I was really happy. Yeah, because of course nowadays like people travel so much more, and the social networks are like if you go to a social network, I'm pretty sure that the average path it's smaller than 6 nowadays. But it's interesting because people came up with this Kevin Bacon thing, and very, very late he figured it out that he was being used in this kind of explanations about graphs. Was quite funny. He was not aware of it, but was nice, and people like, oh, do you know that the scientists are actually using this Kevin Bacon thing to explain networks? He was quite surprised.
Kevin Bacon, if you're watching this, then thank you for your contributions to movies that we can explain networks with you. I've done a fact check. The Lorentz I just showed you was not the Lorentz of Lorentz attractors. Joe in chat's correct. Sorry for the false information. I just worked with a lot of people.
Yeah, one thing about what you said, like going back on time, it's like one of my favorite hobbies, which is like going to a website where you can see like the advisors of your advisors and their advisors and their advisors. It's beautiful. It's beautiful. Like if you guys have time to do that, please do, because then we see that like if today we study, I don't know, physics, there is a very high probability that the advisor of advisor was like Faraday. Like these huge names is really. Then we started to see why some scientists they are still very popular nowadays, because indeed, like. We see like the triangle of people. Then they go like Faraday. Then we see like many other important names in physics, and then at some point we go back to Galileo and then Newton and so on. It's really beautiful. I love to do that and to see like the advisors of my advisors, and there is, I think it's math archaeology project or archaeology project.
There's a math genealogy project.
Yeah, indeed. Yeah. Genealogy project. I love that thing. I like one of my hobbies to be like searching, backtracking where about this how interesting it is that as we go back in time, we see like a lot of like very important people on this tree. It's quite interesting.
Where are we going? We're doing what next?
Yeah. Sorry.
Next slide or?
Yeah. Let's go to the next slide. Yeah.
What's this?
Yeah, ooh, okay. I think it has to do with Erdős. He was the first person that would be like, okay, instead of studying graphs, or in case of I say networks, but in the maths people call it graphs, I'm pretty sure. How do we start to think about these connections, these edges, in a probabilistic way. And that became really interesting, because what happens is that people started to give, like they would just have these vertex, these dots, and they started to connect points with different probabilities. And then we have what we call like when, depending of the probability, we can have this small world phenomenon where we have this 6 degrees of separation, which it's quite interesting, because if we don't know for sure that we're going to be connected to everyone else, we're gonna have this this probability of connection. But then when we start to walk on the graphs, like going from one point to the other, the average path is always usually the same or really close. So it's like if we would map this like the network of Hollywood stars in the past, we would probably find 6 as the average number of edges you have to walk to arrive from one frame to another. And then with Erdős, people started to think about, okay, if we're going to start to have these nodes with probabilities, once we have once we have everyone connected, how I find a way that I walk on this graph in an optimized way. And then things get really like computer sciencey, because we are always asked actually to try to come up with new algorithms to solve that. Like if you are a driver of a delivery service, and then you have to do like a delivery in a lot of houses, right? Like, what is your strategy? Will you also go to like the closest house, then you do the delivery there. Then from this house, you see, okay, what is the next closest house? Then I go there, and you always use this like, what is the closest place? The closest next place on this list is this one. And then this is one strategy that you can use. Another one that what we do with in computer science is trying to find a little bit more of a smart way where we have the computer to do the path beforehand, and then if it's too long, we just give up and let's try something else. There is actually like a set of algorithms to do this kind of work, but it's very interesting how this today is like something that saves millions in time that people need to do deliveries. Just imagine like how important is that to do the deliveries on time. Imagine like these places that you can buy stuff online and have it delivered the next day. Like they definitely pay attention on this kind of thing, like how can we navigate on this map on the most optimized way. Some problems, you have to leave your start place and you just try to go over all the vertex without repeating it. And sometimes you even have to return to the initial vertex. Sometimes is what we call the average path. It's like you have to leave from one node to another, find the optimized way. Sometimes you have to leave from a node, you walk in all other nodes without repeating it, and then you come back.
Oh, so this is like when I do my online shopping or something. They've got to bring a van, and maybe it does some other local deliveries if there's some short range connections between nearby other people who want their shopping. But maybe it's occasionally got to go back to the depot and restock, I suppose, and then go off. And maybe it's more efficient for it to do a cluster and then go and do a separate cluster. Can we talk about the pictures that you've put on this slide? I've been trying to work out what's going on in these pictures. I think there's PS, which I think might be a probability for short range connections. You've got some points on a circle. PS looks like short range probability of connection, which over here is 1, so they're all definitely connected to their nearest neighbours. And over here, it looks like it's less than 1, so we're missing some of them. And over here, the short-range one's a bit lower. And separately, some long-range probability. Is beta, by the way, is beta something like the ratio between long-range probability and short-range probability?
Yeah, they do have a relation indeed. It's a probability where you can actually, instead of only analyzing your neighbors, you can actually analyze, you can actually be connected to any other. It is somehow a probability that you can be connected to any other node, not only your immediate or size 2 neighbors.
Okay, so something to do with PL, this long-range probability, which starts off as 0 in this picture on the left. We get this nice, very pretty regular graph, and then you've got some larger probability that you actually get those connections. So we get a few of them, and then over here we get quite a lot. And I see. So beta being 1, maybe that means that these are now equal probabilities, perhaps. Is that
Yeah.
what you think? Okay.
Yeah. Yes. These parameters, they are the things that we try to calibrate when we are trying to use these models to explain, for instance, how something like the COVID was able to spread so fast. So what we do is like we come up with a network model like this one, and then we try to calibrate these values as we observe the data. Yeah, there is some connections. For instance, we can think about a person who works in one city but lives in another one. So this person can be is connected to its nearest neighbors, let's say people in the city or people in the same household, but this person also have like this capacity to be connected to people in a completely different city. So sometimes we want to model this thing in the same network.
I see. So you could set up something like this, and this would be a kind of model, not actually. You haven't got a list of actual named people whose connections you're monitoring, but this could be a sort of model, mathematical model of what that's like. That you've got some nearby clusters where it's very likely they're connected, and then I see just a few of these like long range putting other people in contact with each other. So not just the naive thing maybe would be just have everyone on this right hand one, where everything's equally likely to happen. You could maybe do some model where some of the edges are more likely than others. Some of the connections are more likely. I see. Okay.
What we're gonna have on nowadays, this is made with it's more advanced algorithms on the suggestion of friends in social networks. So like today, there are many other things that are considered. Not only like if you're a friend of my friend, you are probably my friend. This is like the basic idea, but on the first versions of those systems, it would be something like this. Yeah, if you are my friend, so the friend of friend is always a suggestion to also be a friend on social networks. But yeah, today there are other things that are also on the consideration. But the basic idea is this one. Like this is why we start this model with probabilities. Like this is why on the beginning of the when we start to prepare the model, we start with probabilities and not actual connections, because every time that we execute this model, we're gonna see a different distribution of edges. If it makes sense.
Okay, but you've got some sort of control parameter, which is this beta thing, which controls kind of whether it's short range connections or long range connections or both, and then you just vary that. So you can generate lots of random graphs like this that might or might not have particular properties, but you could then talk, I suppose, about the probability that you have a particular property.
Yeah, this actually makes the problem. This is the kind of problem that I work now, which is like, okay, what like how can we come up with those parameters if we are dealing with probabilities, right? And then it's really fun because of course every time that you run the model, you are dealing with probabilities. So when it's runtime, like you ask like, hey, is there a connection here or not? You don't know beforehand this probability. So you will always have a different model. So what we do is like we run the same model hundreds or thousands of times and see like in average how these connections actually happened.
Nice. Okay. Next slide or no? Or...
Yes.
Okay, let's. Aha, they're good. Somebody in chat did ask, what's the applications of this?
Many. For instance, I think I will give a little bit of explanation on the next in the next slide. But in this case, just imagine that we need to come up with vaccine police or a vaccine. It's not police, it's like law or something. I don't know the word, I forgot. But it's like we need to give guidelines of like which groups should receive vaccine first, for instance.
Okay.
So we will prioritize the groups which have higher probability to have long connections. Because if the groups which have like very low number of connections, or they are always connected with the nearest neighborhoods at most, they are not the spreaders. The ones that do the long distance connections are the ones that we should care about first. And then if we go a higher level higher, we can think about airports. Yeah, how can we improve the network of airplanes to make sure that people can move across the country and it's efficient in terms of gas, efficient in terms of flights. This kind of algorithm is used on the situation in the situations. Just imagine the transportation of goods, transporting things. If it needs to go by truck, for instance, there is like a time dependence there. So we do need to find ways that we find optimized path. Like to start with, I think this is there is a very famous epidemiology model which basically works with this kind of things that we are talking here. What is the probability? Like if you know beforehand the probabilities, then you can come up with ways that you study how the disease will actually spread. Is very interesting because you can tweak these parameters and see how a very small change on those parameters make like very different outcomes. But it's like a lot of applications.
Okay, nice. Yes, what's this Google
Okay.
Maps thing that you've got on the slide?
Yeah. So I I was thinking about indeed some applications, and then yeah, I think most of us at some point we did use Google Maps. And Google Maps have the option that you actually add stops on your walk. It's not like just for A to B, but you can actually you add stops on your way, and then Google Maps tries to put together what is the most optimized way. And this is like a very basic use of these algorithms. And yeah, I love how Google Maps put these things together is quite impressive. But one thing that I wanted to say, I don't know why, but I found important, is that there is a movie called Lion. Have you watched it, James?
I don't know what this is. Sorry, tell me about Lion.
Yo, you will love it. You will love
Okay.
it. It's a very touching movie. It's based on a real story, and like the book is on, at least it's probably on. Yeah, the book is on the left, and the movie is on the right. It's a real story of a guy from India that he he got lost. And then he ended up in a foster care home, and he was adopted, if I'm not mistaken, by an Australian family. And then, yeah, he lives his life. When he's an adult, he decided to find his family again because he was not given for adoption. He was lost, and he uses Google Earth to try to find his family back, and he actually does. And the way that he does, it's like pure maths, but like very natural, very natural. So what he only knew that when he was lost, he was near to this water tower, and then he just mapped like all the water towers that could have on the region that he was born. He only knew this thing. He was really, really small. And then he started to draw triangles from that from one water tower to another. It's beautiful. Yes. And then I was like, bravo, bravo. Because since he didn't have time to look the surroundings of all the water towers, he needed to find a way to connect them in the most like optimized way. And then he would like just drag the Google Earth, Google Maps like little guy, the yellow little guy.
little street
Yeah,
view.
and then he would go like putting on this optimized path until he finds an image that he remember for his childhood.
Right. Wow.
Yeah, it's impressive. Impressed. But I put here some examples more. Of course, I cried a lot when I watched this movie. It's really touching. But yeah, what I put here was one thing that I saw is like networks are used also to see like to suggest friends that you have in social networks, but also the people that you should follow. So then we go to think a little bit about like the type or like the profiles that show to us to follow. It's sometimes it's really like giving you an idea of the type of things you should see on online. That's quite interesting. Yeah, as I said, like there is a model to study viruses spread, rumors spread. Something that we saw during the COVID, which was like fake news about the vaccine and all things related to COVID. Like there was like a very interesting application of networks because in some studies we could see that the group that wanted to spread the fake news, they have very clear targets, but they were not only target people with a lot of followers, because this is one condition, but you also have to have followers that have a lot of other followers. So the gossiping can actually spread, or like the fake news can actually take form, because you need to target people that not only consume but also share to the network, and then the other ones that share, and then we see like a reaction chain. And networks are also used for cell phone services. For instance, like the cell phones are actually part of a huge grid of cell phones, like a network of cell phones. So when you disconnect from one tower, you connect to the other, and then which tower will be the new one is also based on network path, on network measurements.
We've got about 5 minutes. How should we use it? Should we do what should we do? Should we do the pizza thing, or should we do the Eulerian cycles?
We can try to do I think the idea of the pizza thing is the same one of the Euler. We can definitely go there.
Okay, let's have a look at the pizza problem. If need be, I'll put the Euler graph stuff in the further reading notes. So I think there's other things you wanted to say that we'll maybe put in the further reading notes.
Okay.
That's why we've got further reading notes. Can we skip this concept? We talked a little bit
Yeah.
about path length, of how far away you are
Yeah.
from Kevin Bacon. Degree, like how many followers Beyonce's got. I feel bad skipping your visualization. Can we do the...
Yeah, sure. This is a visualization of the families on the
Game of Thrones, right?
Game of Thrones, yeah, on the Game of Thrones, which I suffered a lot watching, but it's a very interesting thing that we can see that some families, they are really isolated. Some other families, they only have one person that connects their two families. And every characteristic of the node, for instance, there is like this node which knows a lot of people, or it's like the core of the family. But there is also this node that's like not very important by its own, but it's like the node that connects two very important families. So we cannot.
I don't remember any of these people around here, these tiny ones.
I think
far
they are
away characters.
Yes,
Like
yes,
core
and I think
characters.
indeed. And one thing that's very common is like, hey, this person only have two connections. Let's just consider this that's a very secondary character, but sometimes this person connects two very important families. So, like, it's also important to not see your neighbors, but the neighbors of your neighbors. I think that's the point.
Okay, nice Game of Thrones visualization. Pizza problem?
Yeah. Yeah, it has to do a little bit with the Euler problem, because it's basically like you have to arrange people. Yeah, let's suppose you have a party, you invite 7 of your friends, but some of them don't like each other. So and it's like it's mutual. If they don't like, if one person doesn't like, if person A doesn't like person B also doesn't like person A. And then you have to think like, okay, if I have those 7 friends here, is that a way that I can just split them and there is no fight? And then it really depends of who hates who. But can we take a look on the people that hate each other?
You've got 7 people. They're all coming to the party. I like all of them, but they have some existing beef. And your challenge is, well, the question is, can you split these people into 2 groups with no conflicts?
Yeah. So, do you want to leave it as a homework, or I can actually explain really fast?
Okay, we got a couple of minutes. I don't tell them the answer, but
No.
let's see if maybe someone will tell us in chat if.
Okay, sounds good.
No spoilers. They've really just seen it. Okay. Maybe we'll leave this here as well. I think there's a thank you slide, and that's. Did we get to your last slide? I think we nearly did.
No, I think this is the last slide. My last slide is just saying thank you and obrigada. Yeah.
Okay. So graph. I think this is a sort of, no spoilers on how to do this, but I think this splitting a graph up into groups makes me think of coloring problems, where you try and I don't know, if you could split them into groups, then we could get them to wear different coloured hats, and it would be the case that any hatred or any people who don't like each other are wearing different coloured hats. They're in different sub parties. So I think there's maybe a hat colour problem.
Yeah, I think the way you think how to do here is definitely related to coloring. You can extend this thing to coloring, and it's like of course the problem gets harder as the number of tables rise. But I think that's the thing that makes that's really amazing about this, is that you can solve for 2, then you try a way to find for 3, and as the number of tables grow, there are like different solutions, and then you try to come up with a formula.
Right. One person has tried to put people into groups, but unfortunately one of their groups has got both G and Ellie in, so party disaster there. Maybe try something different, and somebody else says, can I just put them each in separate groups? Apparently my friends have problems, just put everyone separately, and that I guess works, but it doesn't. Even by my mathematician definition of a party, that doesn't sound that fun.
Yeah. Let's suppose you're like you have a low budget party. You only
Right.
have two tables, but indeed,
Yeah.
like
Okay.
if I think the person got it right when you have like you put Ellie in one table, you put Frank in another table, right? But then Frank hates G, so G should be to the
Right.
first table, but hey, G hates Ellie.
I see. It's this bit.
Yeah.
It's
So this is
problematic.
not possible because there is like a triangle there. But I was thinking like if it has to be a odd number, which also is related to the Euler problem, because the Euler problem, it's like you cannot indeed connect them because it's odd. It's an odd number of length places. So here you have a
Good stuff.
cycle, but I was wondering if you have something similar every time you have an odd number. But yeah, this is work for you guys, the mathematicians. My work is only is only me laughing and implementing programs.
Okay, challenge for us. When can we? This group of people, too many problems, especially that Ellie Frank G situation. I
Yes.
don't want to know what happens there, but maybe we can come up with a hypothesis or for other graphs or other connections of edges that we must avoid. When can we put them into two separate tables? When is it a problem? Is it always like this, where there's a three-person problem? Probably not. I think I can imagine a.
Yeah, I think if there is a cycle and it's a odd number of people in the cycle, then you cannot do this division by two at least. You cannot put them into groups. I don't know if you can do for three or any, but if there is a formula. But I know for sure that if you have a cycle and it's odd, then there is a issue. Because there will always be this crash of
See.
you not being able to put yeah, people in separate tables.
Harder question then the other way round. If you can't split them into two groups, is there necessarily an odd cycle of pairs that don't like each other somewhere in the graph? I think that way around is not obvious. I just thought about it for less than a minute, so maybe chat can think about that for a sort of homework. Oh, good. I
Yeah.
like it when we give them homework. Just to be clear for
Yeah.
people watching, we're not going to take in your homework or mark your homework. But if you do want to send stuff in, there is a website. There's an email address on the Maths Club page, possibly on screen as well. OOMC at maths. No, that's fine. Anyway, there's a place you can send us stuff if you like, but you really don't have to. When can you split people up into two groups is the question. Thank you very much, Marcella, for
Oh.
network theory. I think we've hit 6 o'clock, which is when we wrap up.
All right. Thank you, James, for
Anything?
the invitation. Thank you guys for your
Thanks a
time.
lot. Thank
Yeah.
you.
Hey, obrigada, obrigada.
Anything you want to tell them at the end before we say goodbye, or should we
No, I just want to thank you guys for the questions. Thank you for your time. I hope you had as much fun as I had. Yeah, and yeah, if you wanna talk about more about if you wanna talk more about networks, just let me know.
Right, you can get in touch with us on the email address through the club. Right, thank you, everyone.
Okay.
We will see you again in 167 hours for another episode of the Oxford Online Maths Club. But until then, it's goodbye from myself, and it's goodbye from me. Have a nice evening, have a nice weekend, take care, enjoy
You
the
too.
maths.
Bye bye.
Bye.
Bye bye.